So it looks like the live stream is working today, which is good. It was working yesterday, so I figured I'd give it a shot. So, yeah. I'm pretty sure. So, embarrassingly, didn't switch yet. I'm still on Comcast. But it seems like they're not throttling anymore. I read an article recently that said they were threatened by the attorneys general of a few like Pennsylvania and maybe some other state for some of their other planned policies, and so maybe they backed down a little bit because all of this was happening at the same time when they're instituting data caps and all kinds of stuff. So suspicious. But anyway, so the moral of the story is, looks like this is working. So we're going to keep doing this, and I will try to come up with a better plan for backup stuff. I know that I did one lecture on Discord, but without Nitro, there's a limit, and so technically not everyone can participate. So that's a slight issue. So maybe I should just buy Nitro and have it as a backup. I'm thinking that might be the right way to do it. Or we can use Blackboard. It's hard to say. Okay, so that's enough about that. So just as a reminder, Project 1 is still out, still good to go. I've just compiled homework 1, so it is ready. I'm thinking, so let's think about it. So let me look up the project due date. Project 1, 341. The project is due March 2nd, which is in 2 weeks. So here's my thinking. So Project 1 is due March 2nd. So I'm going to make Homework 1 due February 25th. Okay, so I'll post it after class today. So, and you'll have basically 1.5 weeks to do it. I think for the other assignments, I'll try to give 2 weeks. But I think that the other thing I'm going to do is try not to have homeworks overlap with project due dates. So I'm always going to try to make the homeworks due Thursdays. That way, and I'll have them due Thursdays at like midnight or something. And the reason why I'm going to do that is because I don't want you to have to ever think about like, oh, I have a project due and I have a homework due. That should never happen, right? So it should only be, it should always be, I'm going to try to always make them Thursdays at midnight. Of course, I can't promise that I'll stick to that just because there might be some other things that come up like spring breaks or whatever. If I'm going to have it due on Tuesday, it won't be a project due date week. So if there's a Tuesday due date, it's different, the same printouts. I don't know what that is. That might be from a different section. That sounds like something Ben would come up with. So, and not you, Ben Johnson. He likes stuff like that, titles like that, so it sounds like him. Yeah, you should be really, really scared of the homework. It's going to be absolutely terrifying. So here's the homework. Basically, here are the problems. I'll just talk about them for a few seconds. Whoa, maybe I need to, hang on. I don't think I recompiled it. There we go. So here's the homework. So the first thing what we're going to do is you're going to implement an algorithm that takes two linked lists and merges them. And so this is the description of the merge, but I'll show you what I mean by the merging operation here. So let's say we have like a little linked list thing, I guess. There we go. I kind of like the rounded edges, and then let's say that here is the next pointer, and then we have a bunch of nodes. I don't know if it's going to be over or under. Who cares? Here we go. So here's linked list 1, and then here's linked list 2. Let's make linked list 2 a different color. Let's make it yellow, and let's make linked list 1 something not too offensive. Let's make it this shade of blue. So basically what I mean by merging the two linked lists is you take this node from linked list 1, let me group it up with this, and you do this, and then you take this node from linked list 2. So basically, I mean, it's going to be something like this, and then you take the next node from linked list 1, and you do this, and then you take this node from linked list 2, if I can click on it, there we go. And you do this. See, it didn't come with it. Oh well, okay. And similarly, you just keep going until all the nodes have been merged. That's what so when you read the description, that's what I mean by all of it. And of course, this one will go at the end. Now you might ask, well, what happens if you're in the situation where what happens when you're in the situation where let's say you have a linked list like this. So you have one linked list that's like this, and you have another linked list that's only, say, 2 elements like this, and you're trying to merge them. Well, you would do the same thing. You take 1, 2, 3, 4, and then you take this one, and then the point is that there's nothing left, so you just take the rest of whatever's left and put it on. So, so even though there's not another yellow node, like another yellow node would go into here. So that's a good question. I actually don't really care. I think it's easiest to do it destructively. So I'm going to say it's easiest to do it destructively. So that's fine. If you make a copy of the original linked lists, that's also fine. I'm not too concerned. Okay, so that's what I mean by merging two linked lists. Is you just take one from the other, and go back and forth until you've eaten up all of one, the other, or both linked lists. Okay, so that's number 1. Number 2 is actually a very quote-unquote simple problem. I shouldn't say it's simple. I mean, I'll say it's straightforward. It's something that is not, not a huge amount of creativity went into this question, but I think it's a good thing to ask just because it's, it's important to practice a little bit with doubly linked lists. So we'll have a linked list class, and I've implemented the linked list struct for you here. So, and basically you can use this struct, and just basically the point is that it has a next pointer and a previous pointer. And so you just have to insert at whatever position it is. And then this describes, right, just insert, if it says position 0, then insert it at the head. If it says any other position, then insert wherever. If it, et cetera, et cetera. So, so you basically just want to insert in a linked list at a certain position, which is pretty standard. I think you guys more or less understand how to do that. It's just a matter of actually like writing down all the details. So basically you just have to think about all the edge cases. There's a possibility that the position could be after the end of the list, at which point you should not do that. Yeah, so I think that's basically it for this problem. It's not a difficult problem. It's just, well, I shouldn't say it's not a creative problem, but it can be a little tricky because you have to keep track of all the different pointers. And I think there's 2 or 3 different edge cases that you could run into. So, yep. Okay. This next one is a pretty straightforward one, just like from lecture. Prove that 7 divides. Really what this means is 7 divides 13 to the n minus 6 to the n. Use proof by induction. So we did something like this in class, and I even gave you the hint that 13 is equal to 7 plus 6. Are you submitting the code on GL? I would like to try to have a GitHub submission for code, but we'll see. I'll decide on that tonight and post how to submit the code. It's possible that I'll just read your code and may not actually compile it, so the point is that you should test your code out to make sure it runs, but you don't actually have a full linked list data structure here anyway, so we're not going to require that it be 100% perfect. We just require that you get you think about the problem and get most of the cases. Typo. Okay, let's fix that. So here's another induction problem. It's almost identical to the Gauss sum problem, so that's why I included it. Here, let me recompile this. This should change from n to I. There we go. So, yeah, so this is the sum of squares. So if you add like 1 plus 4 plus 9 plus 16 plus 25, etc., you should get n times n plus 1 times 2n plus 1 divided by 6. And it's one of the standard Faulhaber type formulas. It's good for induction. It's not so complicated. You might have to multiply this out to see what's going on or factor something else. But it's very similar to the Gauss sum proof that we did in class. So these are 2 mathematical induction problems that are very similar to what we did in class. And I was kind of reminded by a former student who's a TA right now that it's better when I do inductions that have actual computer science components to it. So here's one with an actual computer science component. So you know what the secret is? The reason why we don't ask inductions that have computer science components is because they are generally actually a little bit harder, right? Mathematical induction is the induction part without the hard data structures part. And so there you can just focus on a little bit of algebra. But I think it's good. I think, I'm changing my opinion. I think we should, I know that you don't really know what trees are because we haven't actually taught them. But let me just draw out, just like when we drew out a perfect binary tree, let me draw out, ooh, nice. Okay, let's close that up. Oops. Why is that doing that? Let's see, can we get rid of it? Oh, that seems better. There we go, that's perfect. Okay, so here's a perfect ternary tree. So if you remember a perfect binary tree, there were 2 rules for perfection. It's a binary tree, which means a node can have 2 children. That's what a binary tree means. Ternary means a node can have 3 children. And then there's quadrinary trees. A node can have 4 children. And then maybe you would just say a 5-ary tree, right? Or something. I don't know that you'd actually say a pentanary tree, maybe? I don't know. But what we're doing is a ternary tree. So a node can have 3 children. And so to be a perfect tree, what it requires is that perfection requires each node to have 3 children, in this case, or I'll just say max children, meaning the maximum number allowed, in this case 3. And so that's the first rule. And then the second rule for perfection is that each node, or each leaf node, is at the same height. So I think you need both of these rules to make it work. And so here's the reason why. So here's basically a drawing out of a perfect tree. So let's draw it out. Okay. There we are. There we are. So this is a perfect ternary tree. This is perfect of height, say 2. And so then if you wanted to make a perfect tree of height 3, you would do something like this, where then you would take each one of these nodes. Maybe what we can do, because as it turns out, the number of nodes grows kind of exponentially. I think we could shrink them down like this, and then maybe this would work better. Something like this. Oops. I guess we still have to move this one over here. There just isn't space. Okay, and then I think we can, let's see. There we go. I don't think that perfectly worked, but whatever. So anyway, this is a perfect ternary tree of height, I guess 3 in this case. And so basically now, and you can imagine what a perfect ternary tree of height 4 would be. You would just have 3 nodes coming off of each one of these, etc. And so my claim here is that the number of nodes is equal to I guess it's actually 3 to the h minus 1 divided by 2. So that's another, I think I didn't divide by 2. No. So, okay. Yeah, I think that's right. So, and the reason is, if you remember your geometric series formula for calculus 2, basically that's what's doing it here. So yeah, you want to prove this by induction. And the reason why it's 3 to the h minus 1 over 2 is because that's equal to what? Well, don't worry about that. Just prove it by induction. Who cares why? As I say, and I always say this, is that induction is a proof technique that kind of gets used when you don't necessarily have a perfect understanding of what the actual mechanism is behind it. All you know is like a few rules, and you can kind of prove it from that. So let's check this out here. So it was height 1, right? So 3 to the 1, so height 1 is 1 node. So this is height 1. 3 to the 1 is equal to 3 minus 1 divided by 2, so that's 1. 3 squared is 9, minus 1 is 8, divided by 2 is 4, so 1, 2, 3, 4. Here we have 4 plus 5, 6, 7, 8, 9, 10, 11, 12, 13. So what's the next one? 27 minus 1 is 26, divided by 2 is 13. So I'm going to say, yep, probably right. Right? So I think that's the formula. So basically, that's what I want you to prove, and I want you to prove it by induction. Okay? So that's just some basic induction practice for data structures. And we may not even ever code a ternary tree, But the point is that I think the thing is it's a good example because it's something that you're not going to see a lot, but it's also going to teach you like kind of how to do induction in computer science. So induction in computer science, right? The answer is in math, you do algebra. In CS, it is exactly the equivalent of 3 to the x from 0 to n, yes. So in CS, you draw a picture and argue. So that's step 1. And so basically I've done kind of step 1 here. And then what you do is you write down some equations based on that picture. And then you use the base case. And like basically your picture should have a sub case or sub base case, or what should I say, like a the inductive step picture in it, right? So for instance, if you remember how we did it for binary trees, each binary tree of height h is made up of 2 binary trees of height h minus 1 plus the root node. So that's basically the same argument that you want to do here. But I don't want to say too much more. I want you to actually make the argument. So try to make it a good, rigorous argument. Try it, practice out saying things, try to be precise, and try to make your pictures pretty good. Okay, so, and then the last 2 questions are pretty simple, so not a whole lot there. Here's a stack, here's a queue, push and pop, right? So I'm not going to go over this stuff. This is pretty simple stuff, or NQ, DQ. Okay. So let's begin the actual lecture for today. So yeah, let's talk about the actual lecture, which I think what I'm going to talk about today is basically sorting and big O. And the reason why they kind of go together is because big O is a way. So what is big O? So big O is a way to measure the algorithmic complexity of an algorithm. Yeah, algorithmic complexity, or complexity of an algorithm, I guess I should say. And so it tries to ignore implementation details. And I'll try to explain what I mean by that. It tries to ignore implementation details, and it definitely ignores like hardware limitations. It ignores computer speed, etc. So it doesn't tell you exactly how fast the algorithm is going to run on a particular piece of hardware. What it tells you, and there's a reason why it ignores all of these things. It ignores all of these things because it tries to explain relatively. The question is, relatively, which algorithm will perform better regardless, right? That's the thing, regardless of hardware, implementation, etc. So which algorithm, and the subtext is, as we increase the input size. So whatever that means, right? It could be the length of a list that we're going to sort. It could be the number of elements that we're going to insert into some kind of tree. It could be the number of people in a line. It could be just the size of a matrix. It could be a lot of different things. So input size can be, number of elements, size of a matrix, etc., 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 right? But whatever input size is, we want to have some measure of an algorithm that's going to perform better versus an algorithm that's going to perform worse, etc. So okay. So what is the mathematical definition of big O? And so that's a good question. And And so I usually use the set inclusion symbol. So let me just kind of see if I can find it. Nope. There we go. Keep this up over here. So normally what we're going to say, f of n is big O of g of n. When f of n is less than or equal to a constant times g of n for all n bigger than or equal to some initial n, let's say some initial start n, right? So that's really what it is, right? And so this constant c here is doing some work for us. And so let me explain what the constant c is. So, and for some constant c, generally bigger than 0. So what we mean to do with this is that if all we had was that f of n was bigger than or less than or equal to g of n, right? If this is all we had, well, it does, and I'll show you how. Yep. So here's f of n is less than or equal to g of n, right? So if you think about these two things, what this is just saying that g is an upper bound for f. And so, right, it just means that g is bigger than f. But if we have fn is less than or equal to a c times g of n, where c is bigger than 0, so you can't just multiply the thing by 0, you know, you can't do something really ridiculous like that, and you can't make it negative, so, but we have this. And what this means is that g is an upper bound of f once you multiply it by a constant. And so that it's a little weird to say, but if you think about it, let me give you some examples. So for instance, if f of n, so f of n is say equal to 3n squared, and g of n is, for instance, n squared, then the question is, oh, where'd it go? Come on. Right? Is f big O in big O of g? Okay. And so, and I'll tell you what I mean by in a little bit, but and the answer is yes, because normally you would say, oh, well, f is bigger than g, but here what we get to say is, well, what we can say is yes, because you can set c equal to 4, right? And you might say, well, why was I allowed to set c equal to 4? Could I set c equal to 2? The answer is yes, you can set c equal to 2, but then it doesn't give you the less than or equal to, right? Because 3n squared is not less than 2n squared. So when you have, for instance, here, 3n squared is less than or equal to 4n squared, but that's why this constant thing does what it does. It basically allows us to ignore the leading coefficient, if you know what I mean, which you probably should, because that's a pretty standard. Basically what it allows us to do is we can kind of ignore leading coefficients. And the reason why we ignore, and so you might ask, well, why do we ignore leading coefficients? And the answer is because they are often, if for instance you have a function, and that's equal to the amount of time that your algorithm takes, then the leading coefficient often involves, like if you actually knew how to compute the leading coefficient, it often involves hardware constraints, implementation details, etc. So the leading coefficient is basically the thing that we want to ignore, and so that's why this C is in here, right? This C is in here because we don't care if you're running it on a 286 or an i7 or an i5 or a server cluster or whatever, right? So we want to know which algorithm performs best on any machine, right? That's kind of the thing. So, okay. Okay, so that's good enough for Big O right now. I think that's fine. And I haven't really talked much about the start n yet. And I'll talk about that a little bit. Basically, we can ignore, the starting n allows us to ignore small input sizes. So if for some reason your algorithm performs really badly, and by really badly I mean it performs like 10 times as badly as a really inefficient algorithm, but it only does that for sizes less than, say, like 100. But once you get up to sizes of 1,000,000, then your algorithm wins. That's what we want to consider. We don't care about the early behavior, we care about late behavior. So we don't care about the early behavior, we only care about late behavior of the algorithm, also known as the time function, right? So that's the point, is that we don't really care about the early behavior. Like if it goes really badly for, if it does like 20 times the number of calculations on something of size 100, but it still finishes in like a millisecond, then we really don't care. All we care about is that the algorithm performs better on larger and larger and larger data sets. So, yeah, so let's do a little bit of actual coding now. So let's pull up C-line. So if the early behavior is the best case, then there's other things to say about it. I would say that, so there are times where you actually do care about early behavior of algorithms on low. What my data structure teacher taught me is that, so generally, insertion sort performs best on very, very small lists. So we'll talk about sorting in just a second here. So actually, let's make a sorting, and then let's make a CPP file. Let's make a class, even though we're not going to use a class. Okay. Let me delete the class. Okay. So, let's pull C++ down here. Let's include vector. Include, I think, random. I might have to steal some random code. And then using namespace std and include iostream. Okay, so now that we have this, let's implement a sort. So let's start with selection sort. I think selection sort is probably one of the easiest sorts to think about, so we'll just do selection sort first. And you might think, like, why have I just jumped from Big O straight into sorting? But give me a second to implement the selection sort, and then we'll explain. So let's say that we have, let's do it as an in-place sort. So what an in-place sort is, means we don't make an extra copy of the entire data structure. At most, we swap elements. That's generally what it means. So let's say we have a void selection sort, and we have a vector int reference, so it doesn't make a copy, my list, or my vector. Okay, there we go. So, all right, so now how do we implement selection sort? So what does selection sort do? So, oh, I should have had that pulled up. Good point. Good point, Eric. Why didn't you think to do that? this, and this one. Yep. So basically what does selection sort do? Selection sort, I always call it the find min sort. Okay? And the reason why I call it the find min sort is what we do is we scan the list vector, array, whatever, find the min, swap it to the current position, advance current position. Okay? So that's what we do. And then of course here we start current at 0, and then we do a for, right? And so this is basically selection sort. We start the current at 0, we find the minimum current from the current to the end, and we swap it to the current position, and then we advance the current position plus 1. Okay, so let's look at a sort actually doing its job. So let me pull this up for a second. Here's a graphing calculator. Okay, so here is, let's see, where is selection sort? Click on selection sort. So here we go. So this is an unsorted list of elements. So let's see it sort. And so you notice here what it's doing is it's searching. It's going to find 2, and then it's going to swap them. So you see here it marked this. Okay, swap. Now it's going to look again, and it's probably going to find 3, right? It found 5, and it thinks that's the min. Now it thinks 3 is the min. Swap. Search. Thinks 5 is the min, and it's going to think 4 is the min, and then it's going to swap. Okay. I guess 5 is already in the right position. So here, let's see, can we increase the speed? I think we can. Because I think this is going to be boring. There we go. And so if you're interested, that's it. Okay. And then you see here, all right, cool. So let's finish the implementation of this, and then we'll talk about the whole reason why I'm teaching selection sort is to talk about its runtime. So let's finish its implementation. Well, no, we don't need that. For right, so what this is doing is it's taking care of this part, it's taking care of this part. So now we just have to, so this is taking care of this for loop and this for loop. So now we have to find the minimum position from the current position to the end. So we're going to have an int min position. Yep. And we'll set that equal to current. And then we'll say for int find min equals current. Find min is less than my vector.size. Find min plus plus. And then what we're going to do is if well, so why am I not using an unsigned int? I should probably use unsigned. Okay, yeah, I mean, fine. I guess it'll probably avoid that stupid warning that it gives you. But it's really totally not relevant to what we're doing. Okay, so if the thing at the find min, right? So if my vector at find min is, it's not an optimization. It's identical performance-wise. It just won't give you the warning. Let's see, if find min is less than no, yeah, I mean, I don't even really want to have this particular bit discussion, but no, not really. So What have I done? Why is it not defined? Oh, because I misspelled position. That's what it was trying to warn me about. Okay, so if this thing is less, then we set min position equal to find min. So there we go, we found the min. And then what we do is so this is the find min step, and then what we do is we swap. So at the end here, well, not here. Here we swap. So basically what we get to do is we have like and this is just an int, so int temp, you know, and so we just have to say this is equal to my vector at, what is it, current, and then we say my vector at current is equal to my vector at find min. Min position. That's right. And then we say my vector at min position is equal to temp element. Okay. There we go. So I technically, some people also like the swap function. I think you can also do that. But you know, again, the whole point of this implementation is that we really don't care about the exact implementation details. Okay, so and then since it's a void, what we're actually just doing this in place, so we don't have to return anything. So this should do a selection sort, right? So this is doing selection sort. So now what we want to do is we want to analyze this thing, right? We want to analyze this thing for its runtime. So how do we analyze an algorithm for its runtime? Basically what we do is we will count the number of times, for instance, each loop runs, and we count lines of code that aren't loops, if statements, well, even if statements, basically loops or recursive calls or function calls, as O of 1, meaning it takes a single constant amount of time to do it. So for instance here, this for loop is going to be a multiplier. So what I mean by that is, let's just ask like what the runtime, since this is the innermost piece of code, what is its runtime, right? And so you look at this thing and you say, well, this is a memory access. Here's another memory access, right? And then here's a compare. And then here's an if statement, which is a jump, JL, for jump if less. So, but the real good news is, like, who cares if it's in assembly? Who cares if it's in C++ or Python? The if statement, a memory access, right, takes constant time, and the if statement is constant time, and finally the assignment is constant time. So in here, basically this whole part in here, we would just call this O of 1, constant time. And technically you could say, well, maybe it's O of 4, but remember what I was saying, I think last class, when I gave a hint about big O, is that remember that there's this constant C here. So the tradition, you refer to all constant time things as O of 1 rather than O of 4, O of 7, whatever, right? Because the constant C absorbs it, right? So that's the idea, is that if something is O of 4, then it's O of 1. If it's O of 1, then it's O of 4. Back and forth, it's the same thing. So that's why we won't really say O of 4, we're just going to say O of 1, so constant time. Okay, but that's only this little bit of algorithm right here. What about this thing with this for loop, right? This for loop runs, and so let's say that the size of vector is n, right? It runs like n minus I times, right? Where I is equal to current. Really, it runs n minus current times. Okay? So the total runtime for this would be n minus current times O of 1, which is equal to n minus current times O of 1. So it's really equal to itself. And so finally, I guess what you could actually say is it's O of n minus current, like this, for each run. And you don't even have to be this precise. You'll see that we can actually just ignore this minus current business. But you see that the thing is that it only runs, it starts at current and it goes to the end. So technically you might even have like an n minus current plus 1 or something like that, but you really don't care about that. So, okay. So this is O of n minus current, and then the thing is that how many times does this run? So this runs how many times? From current goes from 0 to n minus 1, so it runs n times. So basically what we have is we have n times O of n minus current, but of course each one of these sets a different current, so really this is kind of like the summation from current equals 0 to n, or really maybe you could even say from 1 to n of this. So, okay, cool. So let's look at this, and we would say that this thing is basically equal to the sum from n equal, let's say I equals 0 up to n of n minus I, like this. All right, so this is basically the runtime. Now, I'm ignoring the O of 1 business. You could also secretly just tack on an O of 1 onto all of this, or you can even make this O of n minus I, like this. But then really what you'd be doing is you'd be just saying that there's some constant, like this. So let me just pull it out, and so you can say that there's a constant like this, which would then be factored out of the whole sum, like this. So you could say you were summing up O of n minus i's, right? Which really in our case just means that there's some constant c attached to the n minus I. But then you know a fact about summations is that you can pull out constants out of summations. As long as that constant is multiplied by everything, you can pull it out. And so I do, and so then we're back to here, right? So, okay. So what is the summation? What is this summation, right? From I is equal to 0 to n of that? Well, if you think about it, the sum from I is equal to 0 to n of n, which is a constant, is n squared. It's actually n times n plus 1, but whatever. And then here, the sum from I equals 0 to n of I is equal to the Gauss sum from last time, so it's equal to n times n plus 1 divided by 2. So actually what we end up with is, in total what we're going to end up with is this. We're going to end up with n times n plus 1 divided by 2 minus, I'm sorry, actually it's minus that, so it's just n times n plus 1 minus this, which is all just equal to this. So let's write it out. So here we go. This is the total runtime with some constant c attached to it. So basically, what we want to say, so this is our runtime, right, is some constant c times this stuff. So my argument here is that selection sort is an O of n squared algorithm. And you might say, well, like, okay, but how do you get O of n squared from this? And so basically what I'm going to say is that n times n plus 1 divided by 2 is really equal to n squared plus n, right? So n squared over 2 plus n over 2. And I'm going to say that that's less than or equal to, say, just 2n squared, right? So this is what I'm actually saying. I'm saying that n squared divided by 2, which is a half of an n squared, plus an n over 2, and n is smaller than n squared, is all less than 2n squared, which is, I mean, I think it's probably true, pretty true, right? Definitely probably true. So the good news is that we can just set the constant c equal to 2. We can set g of n equal to n squared, and then we're good, right? We basically have simplified the runtime of selection sort down to O of n squared. And so, okay, cool. And so why do we care that it's O of n squared? What tells us that O of n, what does O of n squared tell us? And the answer is that as your input size grows, right, you expect the ratio of input sizes squared to be proportional to time. So for instance, if it takes, say, 5 milliseconds to run on, say, 1,000 elements, then on 10,000 elements, you would divide that by 1,000, you would get 10. But then remember, it's an O of n squared algorithm, so we would square this thing. So 10 squared, which is 100, times 5 milliseconds, right? And so our estimation is that this thing would take, what? 0.5 seconds, right? 500 milliseconds. So that's our estimation on 10,000 elements, right? So if it takes 5 milliseconds on 1,000 elements, we should expect it to, say, take a half second on 5 seconds, and it would take, or a half second on 10,000 elements, and then like on 100,000 elements, for instance, times 5 milliseconds is equal to 100 squared, so that's 10,000 times 5 milliseconds. So I guess it would take what? It would take 50 seconds. So that's our guess, right? And so the question is this true, right? Is it true? And I think maybe next time we'll actually do some runtime experiments, but maybe we'll do them now. Let's see. I think, yeah, let's see if I can do them now. I just don't have the timing stuff set up, I think. I guess we could steal code from the projects, the timing stuff from the projects. Project 0. Okay, so they're just using C time and C standard lib, so we'll do that. Okay, and then how are they generating random things? So let's make a test selection sort function, where we put in, which is the size. Okay. All right, so what we're going to do here is we're going to say we want to generate some random elements. you just use rand? Let's say rand mod 1000, just to keep the numbers between 1 and 1000. Right. Okay, so let's say vector int new vector equals, and then for 0, I less than n, I plus plus, right? And then we'll say new vector dot push back, maybe. There we go, something like that. Okay. Why doesn't it like this? It doesn't like this because... Okay, it doesn't want us to use rand, but I don't care. I think that's the one that C standard lib has, so... Yeah, I think that's the function in there, so it's yelling at us about that, but who cares? Okay, so... Alright, and now we just have to do the timing part. So, okay. Let's see here. So start equals clock. And then what we'll do is selection sort new vector, and then we will do stop equals, I guess we don't even need to do this, we can just say cout the amount of time it took to sort n elements was, and then we can just do, we can just do that way, because end minus start. Okay, so I think that's good. I think that's good. We can do that. And so now we just have to go into the main and to mess with stuff. So instead of this, we'll include sorting h. Why does it not like that? What's wrong? Sorting.h not found. Oh, because it's in sorting. Okay. So let's run this thing on, say, sizes of test selection sort on, say, size 10, size 100, size 1,000, and maybe size 10,000. Let's not go to 100,000 yet. So let's see if this thing even compiles, right? That's always a good question. Will it compile? No, because of all the circular linked list stuff that I have in here that doesn't work. Okay, so we're gonna have to just comment out basically all of the circular linked list stuff, because I never actually finished it. If you remember, we never did finish the circular linked list class. I just did it as an example. It has a ton of errors in it. Okay, do we have... Looks like a comment is in the way. Yeah. Okay. Better. Okay. Now let's try it again. Okay. What does it not like now? I think we should be good. All right, cool. Fatal error. Excellent. See declaration of linked list. Remove at position is not a member. Cool. Stop giving me errors from previous things. Oh, God. And now here's the project con. Okay, I give up. I give up. You win. You win. I cannot do this. I cannot do this. I was trying to keep everything in the same project, but if there's a single error on a file that's not even included, it's going to explode. So we can't do it. So we need to let's see if not including them helps. Nope. Nope. Okay, we have to make a new project. It's just killing me here. None of this has to do with this lecture. So, okay. All right. Let's just copy and paste everything from this file. Come on. Come on. Come on. What the? Oh. Come on. Come on, come on, come on. Wasted enough time on this already. Come on. Alright, there we go. Okay. Let's try this now. So, yep. Just couldn't, there's just too many errors in all the files that I never did anything with. So, okay. So it tells us that we took 0 time on 10 elements, which, whatever that means. It took 0 time on 100 elements, so that's under the amount of time that we can consider. So let's just start with 100. And now let's do 100,000 and then maybe 1 million. And that way we will see what happens. Okay. Here we go. So 100,000 is going to take a while, right? I guess this is, oh, you know what? This is measuring it probably in milliseconds. So I think this is at my, if you remember my original completely arbitrary, stupid guesstimate of 5 milliseconds on 1,000 elements, it looks like 5 milliseconds is actually the number that's coming out, because this looks like it took about a half second. So if it takes about 50 seconds, so if it takes about a minute on 100,000 elements, right, 50 seconds, maybe a little bit more, since it seems like it's 598, so we expect it to take somewhere between 500 or what, yeah, 50,000 milliseconds or 50 seconds and 60 seconds, somewhere in there, to do the sort on this. And then 1 million will not finish in this class time, right? 1 million is just not going to do. See, here we got this, and then you look at this number, and it's approximately 100 times this number, right? And the reason why it's 100 times is because you're increasing the number of elements that you're trying to sort by a factor of 10, and it's an O of n squared algorithm, so that means that we are increasing the actual number of things that we have to do by 100. And then I'm going to end the program here, because it's not actually going to terminate. This would take, what, 100 times 50 seconds. So how many minutes is that? That's 5,000 seconds would, or no, yeah, something like that. So 5,000 seconds is like over an hour, right? So this won't finish. This is going to take over an hour to finish on 1 million elements. Okay. So let's implement a different sort then. All right. Let me show you quicksort. Okay, and this is going to be a, so there's an in-place quicksort, and there's the version of quicksort that I'm going to show you. So, okay. So then what we'll do is we'll declare, so how does quicksort work, right? So quicksort works in this way. You make somewhere between 2 and 3 buckets. So here's bucket number 1. And then here's bucket number 2. And so, well, actually, let's just do it all in, well, no, okay, let's do it in 3 buckets. So let's make 2 big buckets and 1 smaller bucket. And the reason why they're bigger is that this is going to be for all elements less than our pivot. Okay, whatever the pivot is, I haven't said. And then here, this is going to be for all elements bigger than the pivot. And so then I like to do this. It prevents a bunch of edge cases that are really stupid. This is all elements equal to the pivot. So it could just be the pivot. Could be something else, right? And so you might be asking yourself, okay, you said a lot about this pivot element. So what the heck is a pivot element? The answer in our case is that the pivot element is going to be the first element in the list, or the vector. And that's it. Pivot is going to be the first element. Now there are problems that this poses. There are reasons not to do this, but for now we're just going to say that the pivot's the first element. So, okay, basically if mylist.size, right, else, I guess we can just return mylist. Okay? And so, okay, so that's one thing to do. So that just makes it so that the mylist has to be bigger than 1 element. Well, actually, let's just make it even. If it's bigger than 1 element, then do this. If it's just 1 element, okay, so then what you do on quicksort is once you do this process where you stick everything into the 3 separate buckets, what you get to do here is you will then sort each one of these using quicksort. So once you partition all the elements into the less bucket, bigger bucket, you sort them using quicksort. So this is a recursive sort. Because if you see what happens here is that this is just what happens at one stage. So the next stage is going to do basically the same thing, except here we're going to have 3 buckets, but they just come out of this less element stuff. And then we're going to also have 3 buckets here that come out of the greater element stuff. You never actually have to sort all equal elements, so technically you can sort it, but you don't have to. And then you just keep going. So then here, you'll have to sort these elements here, you'll have to sort these elements here, and then you'll have to sort these elements here, and you'll have to keep recursing down until you get to 1 element or 0 elements in any particular bucket, at which point you say it's sorted. So then what do we do? Okay, so let's make less bucket equals vector int greater bucket. Wait, no, that's not how to do it. Crap. God, I'm so stupid. I'm using Python. And we'll have a vector int equal bucket. Okay, and so now what we're going to do is we're going to go through, so that none of you give me that compiler warning again. So here, if mylist 0, so if mylist I is less than mylist 0, then we'll stick it in the less bucket. Else if it's bigger, right? If it's bigger, then we stick it into the greater one. And then else it's just equal. And of course we got to stick the pivot in, so So basically, in this case, my list 0 is... so there's reasons not to pick it, but I'll describe what those reasons are in a little bit. So, okay. There we go. And then finally, what we have to do at the very end is we have to merge all of this back together. So what we're going to do is we're going to say new list. We're going to say for int x in less bucket. I don't think there's a plus concatenation like there is in Python. I could be wrong, but I don't think there is. Is there an extend for it? No. Okay. So this is a lot of code to do really something very, very simple. We're just kind of pushing these all together. Okay. And then here we're going to just return new list. But you haven't seen the recursion yet. The recursion happens here, right? So this assumes it's all been sorted. So what we have to do here is we have to sort the less and greater buckets. So let's do that. Quick sort less bucket. So let's say less bucket is equal to that, and greater bucket is equal to quick sort of greater bucket. Okay, there we go. An equal bucket is always sorted. So there we are. So this is quick sort. So let's watch quick sort work. It's a little better in Python because it's shorter. Let's look at quicksort. So let's see what quicksort does. So what is it going to do? It's going to take the first, it's going to take the first element as the pivot, and it's going to look for all the elements that are less than it, which is kind of dumb in this case. Let's actually get a better list. Create a new list, random. That's fine. All right, so, crap. Don't do that to me. That looks fine. So the reason why I wanted this one is because here 25 is the pivot. So all of these elements are bigger. So then you see that what it's doing, this is kind of doing an in-place sort, but it's a little bit more complex than what we're doing, because it requires you to keep track of a bunch of indices. See that it's swapping elements, but you see that what it's doing is it's making a less list, right? So then this is the first less list, this is the first greater list, and this is the pivot element. And now it's going to quick sort the less list. So let's speed that up a little bit. So now it sorted that one using quicksort. Now it's going to sort this using quicksort. And now it's sorted. So right before we go, I want to test out. Let's do a test quicksort. Let's copy paste this thing. Let's test quicksort. Basically, everything is the same except we just want to see how fast things quicksort. There. I mean, really, we could use a function pointer if you were really creative, right? We could do something like this: void test sort algorithm, and you could do something. Well, let's do that next class. Let's not do that right now, because as it turns out, we are running out of time, and I am always taking too long to do anything. So let's test quicksort on these elements. So let's see what happens. Let's hope it doesn't crash, hope it doesn't explode, hope it compiles, all of that. Oh, look at that. Wonderful, wonderful, wonderful. And then I think we still have 1 million elements left. I think we still have 1 million elements left. So let's wait and see if 1 million elements pop up. So you see that it took one millisecond, right? 1 MIBA to sort 100 elements. It took 7 to sort 1,000. So you're like, well, that seems actually not so good. But look at if we look at a 10,000, you remember the 10,000 was is it? Oh, it is 10 million. Yeah, it is. So we need 1 million in there. Let's do it again. So, okay. So I'm going to tell you this without proof because we don't have enough time to prove it right now. But quicksort is O of n log n, where log n is base 2 log. So let's just see if my assertion is empirically correct. So empirically means based on the experiment evidence, right? So is it empirically correct, right? Not is it rationally correct, is it mathematically correct? I'll prove it mathematically next time, but I want to prove it this way. So if I tell you it's n log n, right, then the point is that what you do is you're going to take, in this case, you're going to take, say, let's just do the ratio between 1,000 times log of 1,000 divided by 100, or let's just do 10,000 here, divided by 1,000 times log of 1,000, like this. So the point is that you notice that this is going to be equal to 10 because 10,000 divided by 1,000 is 10, times the log of 10,000 divided by the log of 1,000. Now the good news is that this is the log base change formula. This is a bunch of stuff here. So this is really the ratio of these two logs. And so if you look at it as the ratio of the two logs, this log is 3 times the log of 10, and this is 4 times the log of 10. So it's 10 times 3 log 10 4 log 10 divided by 3 log 10. And so actually the log 10s cancel out, and so what we end up with here is approximately 4 over 3, 40 over 3. So it's not going to take 100 times as long. 40 over 3 is, as it turns out, it's 14.33, or 13.33333, right? So here's the question. Are these approximately 13.3 times the previous one? So let's do the calculation. So 1 and 7, it often, remember, Big O doesn't care about this type of stuff. This doesn't seem quite right. But 7 times 13.3 is 93, so that's not right. So 36 times 13.3, 478. Okay, so what am I doing wrong here? Why is this not correct? So it looks like it's actually much more efficient than our predictions, which is actually not good because I always like it when it kind of confirms our predictions, but it's actually overperforming. I hope I didn't do something wrong, but it looks like it's actually overperforming. Is there a reason for that, or I don't know. I'll have to think about that. Very sad, because it should take about 10 times as long to sort that, but it's not actually doing that. We have to check to make sure that, I think I just have to check to make sure that it's actually doing the right thing. Why does it not like this? Okay. I don't see any errors in the code, but of course that's after a 2-second look. We'll have to check this out. It's about 10 times here, which is fine. I almost wonder what it does on 100 million. And 10 is kind of close to 13. So that's fine. It seems like Quicksort is actually doing too good. Right? It's doing about 10, it starts here to kind of stabilize to about a 10 times performance boost. And the problem with that is that a 10 times performance boost is not 13. So it breaks my argument, right? So that's why we need to do some proof, and I'll need to show you that it's n log n and not actually superior to n log n. But because this looks more like O of n than it does O of n log n. I guess 100,000 exceeded 32-bit memory space. So next time, we'll prove that this algorithm is actually O of n log n, and then we will talk about merge sort, and we'll talk about insertion sort, and maybe bubble sort, and we'll talk about which type of thing they are, whether they're O of n squared or O of n log n, and then we'll talk about more general O of f of n's. And I think that's it for today, right? So I'll release the homework on Discord in just a second, and then I'll release the I'll send out a Blackboard announcement about it. Sorry, I've hammered you. I hate giving out more than one Blackboard announcement per day, but I never really know if the lectures are going to work. So, all right, thanks everyone. Sorry to keep you an extra bit of time. I usually don't do this, as you know, but I'm always going too slow. Okay, that's it for today. Hopefully this made some sense. Hopefully you can kind of understand that we're talking about the amount of time that algorithms take, and of course it had to yell at me at the very end and disprove my point by being faster. So merge sort is better for this because it really performs like almost identically all the time, so it won't give you good or bad performance like that. Okay, I'll talk to you later. I'll talk to you next time. That's it.